going to do is come up with a formula for the total capacitance of this kind of an arrangement. 3 capacitors in series. And when I was doing this sort of thing with resistors, and I had 3 resistors in series, if you recall the current, I had mentioned that the current is the same everywhere in a series circuit. So I always started out with voltage, the Kirchhoff's voltage law. Similar situation here. Even though these things will charge up and then you won't have any current flowing, for the period of time that current is flowing in this circuit, the current is the same everywhere. I1 equals I2, I3, and I4. All right? So you cannot have electrons bunching up in one part of the circuit and not the other. It's a very smooth flow, even though it's short-lived. So that's the case there. However, the voltage, Kirchhoff's voltage law, does hold. So we have at any given time the voltage, source voltage is equal to the voltage across C1 plus the voltage across C2 plus the voltage across C3. At any given time, that's the case. So if I start here, voltage source is equal to those 3 total, and I use that formula, Q equals CV, I can come up with a formula that relates, that includes the value of capacitance for each one of those elements. So VS, V is equal to Q over C, so we have total charge over total capacitance for the entire circuit is equal to the charge over the charge on capacitor 1 times the capacitance of 1 I end up with that. Just made that substitution. And now I make another substitution. Here we have current is equal to charge divided by time, so it's coulombs per second. So charge is equal to current times time. So we have this. And remember what I started out by saying, the current is the same everywhere? So at any given time, the current is the same. So all these guys, current times time, they're all equal, every one. And since they're common to every, even though I have a different subscript, they're all the same, so I can get rid of these guys. They all cancel out. And that leaves this. Okay, that's in your book. Does that formula look familiar? If you think of resistors. So the formula for calculating capacitors in series is the same formula for calculating the total resistance of resistors in parallel. Same formula. So if I have another capacitor here, I just add it in. And when I have only two capacitors, I can reduce this to that special formula that we know about for resistors, which is, you just find the common denominator of those guys, take the reciprocal of it, and you get that formula there. Okay? Let's do the same thing. Can I erase that? Let's do the same thing for capacitors in parallel. So for this circuit, as was the case for resistors, the voltage across each capacitor is the same as the source voltage. And Kirchhoff's current law holds for the capacitors as it would for resistors. So what we're going to do is use this guy formula over here. So we have Q over T. And then I'm going to make this substitution here, Q equals CV. So we have and we know that, actually this is C1, that's C2, C3. So we know that all the voltage across every one of those capacitors is equal to the source voltage. Everything is the same. So, and I'm using T, I should have used S. But these guys cancel too, they're all the same. The time cancels, it's the same. And the formula for the total capacitance for capacitors in parallel is this. It's just resistors in series. So if you know the formulas for resistors in series, resistors in parallel, you just flip them change the R to a C, and you got it. And remember I showed you my little radio here? And you can see that this capacitor, they called it a ganged capacitor. It's just a bunch of plates that are real close together, but they're all in parallel. So you have the plates that are moving in this arrangement, they are all connected together. And the plates that are stationary are all connected together. So that variable capacitor is just, it's like this, where this plate, the top plate's connected to that one, bottom plates are all hooked together. And in this case, in that case, they're variable. Symbol for a variable capacitor, by the way, is this. So if you ever see that, that's a variable capacitor. I have one in my little kit here. It's well, it almost looks like a potentiometer, like a variable resistor. But if you look at it real close, there are plates that are half sort of semicircles, and then when you move that little dial, they kind of overlap. You can look at that. So there's all kinds of arrangements. Okay, so that's resistor or capacitors in series, capacitors in parallel. Let's do a worksheet, okay? Can I get your other one, by the way, your other worksheet? Just so you don't forget the one you did already. Okay. You gave it for reference. Okay. Jared, did you get it?
Yeah, very good.
Okay, very good.
She was like, how did David go with his wizardry house? Like, he said that after they found out, he woke up in his bed. And she looked at me and said, that's not gonna have to leave. So she's like, hey, when he falls asleep, we're gonna wait right there. Because no one's gonna move him. Boss.
Did you record it? I don't know. I didn't know what I said. I don't know what I said.
She woke up in there.
Hey, you know what happened? I remember. I knew it, and he was like, oh, just bring things and look at that. I think I like, you need to do this whole thing, because he posted it, I'm like, that's actually, that's not what we do. That we do. And then I started putting in the stuff, and it's like, nope, see you.
See ya. See ya.
Ready?
Bye.
More time?
Wow.
Not ready? You're ready. You ready, Russell? Alex?
Yeah, Alex.
How about Royce?
Not quite.
You're not quite ready? Okay.
You can start working the first one, should have it done by the time you work the first one.
You're still working on the first one?
No, I said you can start working the first one.
Oh, the first one, okay. So let's do number 1, and then we'll do number 3, okay? Because it's the same formula. Total capacitance, you have 4.7, 3.2 microfarads. They're connected in parallel. What's the total? 7.9. Right?
Mm-hmm.
Just add them together?
Wait. Don't you have to? 7.9, right?
Yep. So for parallel circuits, just think of this plate here, they're all connected.
Right.
So CT is equal to C1 plus C2 plus C3.
Yeah.
Parallel is easy, just add them. Okay? And then number 3, those guys are connected in parallel. 1.2 micro, 15.6 micro, 7.8 micro, connected in parallel. I get 24.6. Right? Number two, what we're going to do is take the 4.7 and the 3.2 microfarad capacitors, and now we're going to connect those in series. So if we do that, we have the formula for resistors in parallel, and I get, just really quick, I'd get 1.9 microfarads. Okay, so remember when we had resistors in parallel, the rule of thumb was that the total resistance is smaller, is less than the smallest resistor. So if you have capacitors in series, the total capacitance is going to be smaller than it's going to be less than the smallest capacitance. In this case, the smallest capacitance is 3.2 microfarads, and I get 1.9 microfarads. At least I know that I'm on the right track on that one. And then in question 4, we got those 3 capacitors in series. I get 0.975 microfarads, which is less than 1.2 microfarads, so I think I'm on the right track there. Anybody get anything different? 0.975 microfarads. So series, there you go, that's the formula. Okay? You definitely, hey guys, you definitely want to write those formulas down, okay? Definitely. Anybody have anything different? Do you want me to go over anything on that? Good to go? Okay. The one final thing that I want to talk about, and then we'll have a multi-sim lab on it, has to do with the response, the current and voltage response that a capacitor creates when it's connected to a DC circuit, when you have a battery with a switch and you close the switch. By the way, if you ever see me, I'm trying to get out of this habit, a lot of times I'll draw a capacitor like that with one curved line. That's the way I was taught. And the reason is that 2 straight lines, if you get sloppy, it looks like a battery. So if you ever see me draw a line and a curved line, that's what's going on, or I keep forgetting. I want to put a resistor in this circuit. Because the formula that we're going to look at has resistance in it. So here we have a simple DC circuit. We got a switch, a resistor, and a capacitor that has 0 charge on it. When you throw that switch, as soon as you throw that switch, the capacitor is going to start charging. But it's not going to charge in an even way. It's going to charge in an exponential fashion. And the reason is, It all has to do with geometry. If you have a capacitor, you've got here, coming out of this battery, you usually have, you've got thin wires, okay? And when the electrons hit that capacitor, they flow onto that capacitor, and it's almost like, the thing that I like to, the analogy that I like to use is that of a sporting event, football, baseball, or whatever, where you're an electron. You're going into that stadium, and let's just pretend you're the first few people, one of the first few people going into that stadium when the gates open. You have one gate going into the stadium. The gate's open. As soon as you go into that stadium, you have, and let's just say it's open seating. You go into that stadium and there's nobody around, maybe a couple people, and you can just go anywhere you want with no effort. And that's kind of like what happens when you throw the switch on the plates of these capacitors, on the plates of that capacitor. There is so much area that the electrons literally flow at their maximum value with almost no work being done. And voltage is a measure of the amount of work it takes to move a certain amount of charge. So there's literally no voltage when you throw that switch across that capacitor. So the voltage starts out at 0. But the current flowing in your circuit is a maximum value at the instant you throw that switch. So the current goes from 0 to whatever the maximum is in almost no time. For all practical purposes, it's instantaneous. And at the same time you have 0 voltage, you have maximum current. Well, as time goes on, the capacitor starts to charge, so the current goes from here to here and starts to drop exponentially. So it's not a straight line, it's a curved line. And over time, as that capacitor charges, the current goes to 0. Well, the voltage, as the capacitor charges, the voltage across that capacitor is going to approach the source voltage. So the voltage across that capacitor will increase like that. So you have two things going on, and they're not simultaneous. Everything that we did with resistors, the voltage and the current were 100% in phase. Voltage goes up, current goes up. Voltage goes down, current goes down. Not so with a capacitor. When you throw that switch, bingo, that voltage goes up exponentially. The current just goes to a maximum value, which is actually equal to V over R. Ohm's law equals V over R. So it hits this value here, this maximum, and then starts to drop. As the capacitor charges, current drops. And you have that kind of scenario. So now the switch is closed, let's just say. Capacitor's charged. You open the switch, your capacitor is charged, it's got a voltage on it. What happens when the switch is closed? Your capacitor is fully charged. Remember, it's like a voltage source. So here you have, I'm just going to redraw that. Like so. So during charging, you have, when the capacitor is being charged up, you have this kind of an arrangement. You have this kind of an arrangement for the current. And I think, didn't I have my battery going, I think I had my negative down there, so the current's like so. So this guy here is negative. This guy here is positive, just from how it was connected to the battery. Now, I disconnect the battery, and I have my switch, and I want to discharge that capacitor. I close the switch. My voltage is going to discharge, my voltage is going to go down like so. Boy, that's not a good curve. It's going to go down exponentially. Like this. The current, let's just say that's the 0 point here. When I close that switch, the current's going to go back the other way, this way. So I'm going to get a spike like this, almost instantaneous transition from 0 to maximum, and then it's going to go up like this as it reaches 0. Charging, discharging, charging, discharging. And the formula for this curve let me write it bigger. Formula for this guy here is let me just verify that. Let's get these formulas wrong. Yep. Now, probably thinking, okay, what in the world's going on? What is this? E. What is that? E to the minus T over RC. What is that letter E? What is that doing there? Does anybody have any inclination of what that is? I want to go over that with you. This kind of an equation, it's all of a sudden, when you start doing exponential equations, you know, it's a whole nother world. We're introducing calculus and differential equations. It's not easy to come up with that. I'm not going, and this is basic circuits, I'm not even going to try to come up with it. But I do want to go over with you what this number is. It's a number. E is 2.718281828. It's an irrational number. Remember last week we talked about irrational numbers. They are numbers that you cannot express as a fraction. So pi is an irrational number. The square root of 3 is an irrational number. You can't express it as a fraction. The square root of 2 is an irrational number. And that is an irrational number. And it's when we get into inductors, you're going to see it. And it can be intimidating. So I just want to talk about it a little bit. This is not in the book, but I just want you to understand a little bit about where it comes from, because after all, there is a key on your calculator with the letter E. And when you press that key on your calculator, you're going to get that 2.71828 whatever. And you really should know a little bit about it and where it comes from. Okay, can I erase this or not? Can I erase that? I'll keep it there. I'll just work over here. So the letter E, the irrational number that we call E, similar to pi. Pi is an irrational number as well. No one really knows for sure who first discovered this particular number. But it does go back to the 1600s. And we do know from manuscripts that a Swiss mathematician by the name of Jacob Bernoulli was the first person to work with the number that we call E. And if you're mechanical, maybe you have heard of Bernoulli principle. He did a lot of work in fluids, liquids and gases and whatnot, and he did a lot of experiments there. But he had a particular interest in banking, and he wanted to know, he was curious about how much money you could make from compounding if you put money into a bank. All right, so I want to just develop that concept with you, because the number that we call E actually started out with an investigation into the principles of compound interest. 1600s. So if you put money, let's say you had a Bank A, and they were advertising that they would pay 100% interest if you put money in their bank. And they would pay that interest, they would compound it one time a year. And if you kept your, I'm going to just assume that we put $100 in Bank A. And they said, if you give us $100 on January the 1st, then on December 31st, we're going to pay you 100% interest. So after 1 year, you would have $200, right? So they're going to give you have $100, they're going to give you 100. After 1 year, you're going to have $200. Okay? Bank B says, we're going to do the same thing. Hope I get this right. I haven't done this analysis in a long time. Bank B says, we're going to do the same thing, but we are going to, you give us $100, we're going to pay you 100% interest, but it's going to be compounded twice a year. So we'll pay you 50% on June the 30th. We'll pay you 50% on December 31st. Okay? So on June the 30th, you have $100. They're going to give you 50% of that, 1.5, and you have $150 on June the 30th. Okay? Now on July 1st, you're starting out with $150, and that's compounded for another 6 months. So on December the 31st, they're going to pay you that other 50%. And that comes to what? $225. I think. 225, I want to make sure I get that right. I don't want to mess up here. Okay, that's Bank B. Bank C says we're going to do the same thing, but we're going to compound your money 4 times a year. So Bank C says at the end of March we'll pay you 25%, at the end of June we'll pay you 25%, the end of September 25%, December 25%. So you have this. You have $125 at the end of June. You have $156.25 at the end of September. You have $195.31. And at the end of the year, you have $244.14. Okay, so you can see that by compounding, even though the banks pay the same amount of interest, the amount of money that we make on our $100 keeps going up. All right? So I just have a little table that I did a while back, and if you were to compound 100% every month, so you have 8.33% per month, at the end of 12 months, you would have $261. So that's 1.0833 raised to the 12th power, because that's all I'm doing here. I'm saying this is 125, this is 125% or 25% interest times 1 times 2 times 3 times 4. So I'm going, the interest rate would be 100% divided by 12 raised to the 12th power, because I'm compounding once a month. And I would end up with, how much did I say? 261. 261.30. And so if, one more example, if you took that $100 and you compounded every day, you would get 271.45. $271.45. Okay? So we go from 200 to 225 to 244 to 261 to 271. 45. Well, guess what's happening? You see these numbers? See this number, how they're increasing? If you, I'm using $100, but if I instead used $1 as my starting deposit, I'm getting closer and closer to that number. So what Bernoulli did using compound interest, he asked a question, a real simple question. He said, how much money can I make if I put $100, or if I put $1, whatever his unit of currency was in Switzerland, if I put $1 in the bank for 1 year and compound it continuously, not every minute, not every second, but continuously. You can solve that problem using calculus. But the formula that he came up with is this. It's basically the formula that you see for compound interest, except where I have a 1, you'd have an interest rate. And here's the formula he came up with. And the limit of that formula as n approaches infinity. The limit of that formula as n approaches infinity, as this number, I went from 1 to 2 to 4 to 12 to 365, is equal to E. is equal to 2.71828, 1828, etc. Okay? That's where that number comes from. Now, big deal, so what? So he did this experiment and he came up with that number. Why is it that that number deserves a separate key on your calculator? If that's the only time you end up using it, why is it that it has a separate key on your calculator? Well, the answer is it appears all over the place in science and engineering. If you obviously were using that number here on the charge of a capacitor over time, we're going to see that that number E appears when we get into inductors. In microbiology, in some cases, not all cases, but there are certain bacteria when you put, you know what these Petri dishes are for growing bacteria? They're thin dishes with a protein inside, and they look like a pancake. And microbiologists or researchers put a little drop of a bacteria or whatever inside there, and let's say that maybe it's a virus, I don't know, they want to grow it so that they can come up with a vaccine. So they'll get a little bit of this bacteria or a virus, they'll put it in there and it'll start to grow because they have the dish has a covering of protein, food, on the bottom. What they found out is that in many cases, the rate of growth of that bacteria is a function of the amount of bacteria, the number of bacteria cells at any instant in time. And the rate of growth ends up to be this. It ends up a curve. The growth rate is a curve that looks like that portion of that curve. So the number E shows up in microbiology, medicine, engineering. It shows up in equations that have to do with expansions of galaxies, so astronomers use it. It's all over the place. And so, deservingly so, there's a button on your calculator. When you push it, you get that number. All right? That's where it comes from. All right, made it. Good deal. So, we don't have to know any more about it than that. If anybody asks you, you know a little bit about where it comes from. Now, let me just point out a couple things on these formulas here. If you look in your book on page, what? Page 405, you'll see two formulas that are the general formulas for the charge and discharge rates for a capacitor. They include, like I said, they are general formulas. So how do you get from those formulas to this one? How do you get from the general formula for current to this specific formula? What you have to do is decide whether you're charging or discharging. And for example, let's just look at this. Here's the formula for voltage in your book. They have the letter tau, the Greek letter tau there, I'll go over that. So that's the general formula. So that's the formula that's valid for charging or discharging. So for a situation where we're charging, we know that the initial value for voltage is 0. It's 0. So V of 0 is, so this guy here is 0. So the formula for the voltage over time is equal to VF minus VF e to the minus T over RC. Well, if you factor out the VF from each term, you end up with 1 minus e to minus T over RC, which is this guy here. So if you use, now I'm not going to get into this in any test, but I don't want you to be confused by what's something in the book. So you look at the general formula and you say, okay, what are my initial conditions? And then you look at the general formula and you say, okay, voltage, the initial condition is that V initial is 0. You cross that out, and then that gives you the formula for charging, the charging voltage, the voltage during charging. Okay, that's how you use those. Same way with current. In the book, I have RC, they have the Greek letter tau, and this is called the time constant. RC, resistance multiplied by capacitance, is equal to time constant. What exactly do they mean by that? Here's what's going on. Even though the charging and discharging curves of this circuit take this shape, they could be, if this is a huge capacitor and a huge resistor, this time scale could be stretched out for a much longer, a much wider scale than it is shown. So the charging time for a circuit where you have a large capacitor and a large inductor, you could have voltage here, you could have time here, and it could go up real slow, something like that. Okay? So what we say as engineers, in mathematics, if you were to solve this equation mathematically, the voltage, the maximum value for VT, it would never ever reach the battery voltage. During charging, if you were to have, if you had a battery here, let's go back to our initial conditions. So if we close that switch, and this capacitor starts charging here, it never really hits the maximum. Mathematically, never hits it. But in engineering, we're not concerned about the curve reaching 1/1,000,000th of its maximum value. We don't care about that. What we say is that when the time equal to 5 time constants has elapsed, 5 time constants. So when tau is equal to, so when you've got 5 times t, 5 time constants have elapsed, that capacitor is fully charged. And so like if this were, and by the way, if you take resistance in ohms, and you multiply it by capacitance and farads, and you break it down to the basic components in terms of joules per second and volts and coulombs, all that, you end up with seconds. So R times C is equal to seconds, so you have seconds on the numerator of your exponent, seconds on the denominator. And you always have to have that. You cannot have an exponent with dimensions. It has to be a pure number. So if you take 5 times RC, that's when the capacitor is fully charged. 5 time constants. Okay, that puts you at about right here. And that's something you want to remember. As engineers, we're pretty practical. We say that when 5 time constants have elapsed, that's it. That capacitor is fully charged. And in the book, they represent this RC by the letter tau. So I just, there. But that's what that is. Okay, so if this is, let's just look at this. If you had a 1 kilo ohm resistor and a 10 microfarad capacitor, the time constant is RC. That would equal 10 cubed. And this is 10 times 10 to the minus 6th. So tau is equal to 10 times 10 to the minus 3, or 10 to the minus 2. So in 1/100th of a second, that's 1 time constant. So that capacitor will be fully charged in 5/100ths of a second, which is pretty fast. 5/100ths of a second. See that? Those capacitors, huge capacitors that I had here, the time constant of something like that might be a couple of milliseconds, so it would take maybe a half second to be fully charged, something like that. And if you really, actually, it depends on the resistor that was connected, but if you really had a huge resistor, you could end up with an RC circuit that takes 15, 20, 30 seconds to charge up. It takes a long time to charge. Does anybody have any questions on it? Like especially this letter E? Something that can be really confusing. I wouldn't be intimidated by that. That's just a number. The RC time constants. Okay. Let's do a multi-sim lab here. And what we're going to do is just item 1. Item 2 is I'm going to have you is building the circuit. We're just going to do item 1, which is multi-sim. Create an RC circuit. Look at the time constants. And on this one here, you're going to be connecting the oscilloscope to the circuit. And I'll show you where that is on your multi-sim if you don't already know. You'll have a screen there with an oscilloscope.